Good morning, everyone. I'm Xiangyu Zhu from Institute of Automation, Chinese Academy of Sciences. Today, I will introduce our work on phase alignment across logic poses. Phase alignment is to find the phase shape which is always modeled as a set of semantic facial landmarks such as eyes, mouth, and nose. It is fundamental for many applications like recognition, 3D animation, and makeup. After 20 years of developing, phase alignment has achieved many practical methods from ASM to the currently popular cascaded regression. All the landmarks are visible and can be detected. The yaw angle of phase is below 45 degrees. Inevitably, there will be some landmarks become invisible and cannot be detected due to self-occlusion. We call this phase alignment across large poses, where two additional questions should be answered. Which landmarks are visible, and where are the invisible landmarks? There are three challenges to solve this task. Firstly, the model challenge. In large poses, phase shapes cannot be modeled with a single landmark configuration, so multi-view framework where different landmarks for different views is always adopted. However, this method highly depends on pose admission and it needs too many landmark configurations in unconstrained environment. Secondly, so we need a unified model to describe phase shapes in all poses. Secondly, the fitting challenge. When the face is close to the profile views, there will be dramatic appearance variations from full face to half face. So we need a stronger regressor to cover these larger appearance variations. And finally, the data challenge. Manually labeling landmarks on large pose faces is very tedious since the occluded landmarks have to be guessed, which is impossible for most of people. So most of public available databases such as 300W are collected in medium poses. Few large pose databases like AFLW only contains visible landmarks, which is ambiguous in phase shape and hard to train a unified phase alignment model. So we need fully labeled data in large poses. Next, I will introduce our solution to these three challenges. Firstly, to resolve the model challenge, we intend to use the 3D model instead of the facial landmarks. The fitting objective will change from the landmark positions to 3D MI parameters, including scale, rotation, translation, shape, and expression PC parameters. We complete fitting by estimating these parameters, and as a byproduct, the landmarks can be sampled from the fitted 3D face, and their visibility can be easily gotten through 3D geometry. Secondly, to resolve the fitting challenge, we combine the convolution neural networks with a cascaded regression. Okay, let's take an overview. Given an initial parameter P0, we construct a specially designed feature, PNCC, which we will introduce later. We stack it with an input image and send it to CNN. The CNN outputs a parameter update delta P0, which to generate a better parameter P1. And afterwards, the next iteration begins. To realize this cascaded CNN, two problems need to be solved, the input feature and the cost function. Let's start with the input feature. The main purpose of the input feature is to provide CNN with a 2D location of each model vertex. Besides, the framework of cascaded CNN has three requirements on its input feature. Firstly, the input feature should depend on its output to enable the cascade manner. The convergence property requires that the input feature should be discriminable when the fitting is complete. And the convolvable property requires that the convolution operation on the input feature should make sense. So we design our features as follows. Firstly, the feedback property. Firstly, we normalize the 3D mean phase to 0 to 1 in x, y, z axis. The unique 3D coordinate of each vertex is signed as a 3-channel vertex index called normalized coordinate code, NCC. In the case iteration with a parameter pk, we construct a 3D face and adopt the buffer with NCC as its texture, generating the project normalized coordinate code PNCC. which is then sent to the input of CNN. From PNCC, the network can easily know the semantic meaning of each pixel directly from its color. And regarding the three properties, firstly, the PNCC depends on CNN output PK, so it fulfills the feedback property. Next, when CNN detects that each NCC superposes its corresponding pattern, the cascade will end, so it fulfills the convergence property. And finally, the PNCC is smooth in 2D space. The convolution indicates the linear combination of NCCs on local patch, so it fulfills the convolvable property. Next, let's introduce the cost function. Note that the CNN output is 3D-ML parameters. Naively, we can directly penalize the distance between the CNN output and the ground truth parameter update. Unfortunately, parameter error is not always equivalent to the lamp error, since these parameters contribute to the final 3D phase in a cost-to-fan manner. Specifically, from the mean 3D phase, we rotate, scale, and translate it with pose parameters. Note that at this stage, the fitting has been fairly accurate. Then we move the phase with pressure PCA and shape PCA. Obviously, you can see that pose parameters are the most important during fitting, followed by the expression parameters and shape parameters. To model this priority, we weight each parameter arrow to make CNN concentrate on a subset of high priority parameters. We propose the weighted parameter distance cost, WPDC. In this cost, the weight of the ith parameter is evaluated by the lambda error brought by its misprediction. In detail, suppose the current network predicts the parameter picker, the ground truth parameter is PG. Our purpose is the weight of the yaw angle. In the ground truth parameter, we replace the ground truth yaw angle with the current yaw angle and reconstruct the 3D phase. The error between the ground truth 3D phase in B and the missed yaw phase in C is evaluated as the weight of the yaw angle, and the other weights are computed in the same way. We can see that larger lambda error gives larger parameter weight, which further means higher priority during CNN training. In this figure, we can see that by incorporating the weights, the lambda error is reduced by 60%. Finally, I will introduce how to solve the data challenge. Given label landmarks, we can get accurate 3D phase with landmark-based 3D-ML fitting. And we mark some anchors on the background and simulate their depths with their nearest phase vertices. Afterward, the whole image can be turned into a 3D object through triangulation. When the image turned into a 3D object, it can be rotated in 3D space and rendered at any larger poses, generating a series of virtual phase images. We call this phase synthesizing method as phase profiling. In the experiment, we increase the yaw angle at a step of 5 degrees until 90 degrees, enlarging the 300W data size to 120,000 samples. And more importantly, we get labeled data in large poses. Okay, let's see the experiments. We train our cascaded CNN on 300 WLP, which only contains synthesized samples, and test it on AFLW, which contains real-world large pose samples. We compare our approach with currently popular methods, including CDM, RCPR, ESR, and SDM, and report the normalized mean error. We can see that, firstly, all the methods benefit much from the data synthesis, especially in large poses, which demonstrates the fidelity of our phase profiling. And secondly, our method reaches state-of-the-art above all the 2D methods, especially beyond the medium poses. The minimum standard deviation also demonstrates the robustness to pose variations. Here are some examples of fitting results. We can see that our method can well handle profile views. In conclusion, to solve the problem of phase alignment across large poses, we propose to fit 3D-MM instead of detecting landmarks. Then we seek to cascade CNN to finish the 3D-MM fitting task. And finally, we propose a phase profiling method to synthesize large scales of data to train our CNN. Thanks.